In this lesson, I'll show you how to solve electrical problems by the Laplace transform. This is question number 5. The question reads, a switch is closed at t is equal to 0 and there's no initial charge on the capacitor. Write an expression for the current. Notice that we are working with a DC source. We have a battery here that's supplying 75.4 volts. And at time 0, this is switched to on. Now, according to Kirchhoff's law, which is stated right here, the sum of the voltage that drops across a resistor, an inductor, and a capacitor, we have all three here, in an electrical circuit must be the same as the voltage source applied to the RLC circuit. That being said, we have 75.4 is equal to the voltage drop here, which I'll represent as resistance times the instantaneous current, plus the inductance times the rate of change of the current with respect to time, plus for this one, we can represent that as 1 over the capacitance times the integral between 0 and t for the current I dt. The equation that you see right there is a differential equation that represents this RLC circuit. Next, what I'll do is I'll take the Laplace transform of each term in this equation. I'll take the Laplace transform of 75.4. So I'll write down Laplace transform of 75.4 is equal to the Laplace transform of r times I. R is equal to 225. 225. So 225 times the Laplace transform of I plus the inductance is 1.5 henries. I'll write down 1.5 times the Laplace transform of I prime. This expression and this expression mean the same thing. Di over dt is d prime. Plus 1 over c, and our capacitance is 4.75 microfarads. So I'll write that as 4.75 times 10 to the power of negative 6. And since we're placing this inside c, 1 over this expression is the same thing as 10 to the power of 6 over 4.75. And taking the Laplace transform of an integral can be represented like this. The integral between 0 and t, I dt. Now I have to find out what the answer to each of these are. This one is easy. It's a constant, so we take 75.4 and multiply it by 1 over s. 75.4 divided by s is equal to, I'll leave this the way it is because in my next step I need to isolate for it, plus 1.75 times the Laplace transform of a first derivative. For that I'll use this expression. So I'll introduce brackets. S times the Laplace transform of our function, that's I, minus the current at time is equal to 0. That's equal to 0. So I won't write down minus 0. I'll just leave this the way it is. Plus, now we find the Laplace transform of an integral. That's easy. You write down 1 over s times the transform of I. That's being multiplied to 10 to the power of 6 over 4.75 times this expression. Now we need to solve for this term and this term, and we can do that by factoring. So I'll factor out the transform of I on the right side. On the left side it stays the way it is, 75.4 over s is equal to the Laplace transform of I, bracket 225 plus 1.5s plus 10 to the power of 6 over 4.75s. Now, if we divide both sides by this expression, we will end up with 75.4 as the numerator, all over s times 225 plus 1.5s plus 10 to the power of 6 over 4.75s at the bottom. Expanding the bottom, and remember, the right side is the Laplace transform of I. If I expand this, I still get the same numerator, except now I have 225s plus 1.5s squared. It appears to be a quadratic. S times this expression gives us 10 to the power of 6 over 4.75. Now, since this is a quadratic, we can probably match it up with an expression in this table. Let's see if we can. You'll notice that there are some quadratics over here. So if we can somehow complete the square for the denominator, we can probably match it with the transform of 23. So with that said, what we can do is make this so that we have s squared, and I can divide each of these terms by 1.5. This will remove the 1.5 here, and I'm only doing this because we need to complete the square. It's always nice to have s squared without the coefficient in front of it. Dividing this by 1.5, I get 150. And dividing this by 1.5, let's find out. We have 10 to the power of 6 over 4.75, and then dividing it by 1.5 gives us approximately 140,350. Since this is three significant figures, I'll only work to 3 here, so I'll use a 140,000. 140,000. Also keep in mind that in a later step, I'll be dividing 75.4 by the factor that I pulled out of 1.5. I'm not going to show it yet, but I'll do it in a later step. This is equal to the transform of I. I want to rewrite this so that it looks nice and clean. 75.4 over s squared plus 150s plus 140,000. Completing the square isn't hard. I'll show you really quickly. You take 150 divided by 2. That gives you 75. 75 to the power of 2. That I need my calculator for. 75 to the power of 2 is equal to 5,625. 5,625. You add and subtract 5,625 to this expression plus this number. And this becomes a perfect square trinomial where we can write it as s plus 75 squared, and this number minus that number gives us, let's use our calculator, 140,000 minus 5,625. This gives us 134,375. Take a look at the transform. They want b to be squared, so I'll square root this, and I get approximately 367. 367 squared. And in the denominator, we have 75.4 divided by 1.5, because I removed that. 75.4 divided by 1.5 gives us approximately 50.02. Now, according to this b and this b need to be the same. So this number and this number need to be the same somehow. That's not a problem. What I can do is make this 367 and multiply this by 1 over 50.2. So when I write out my function as I is equal to e to the power of negative a, and our a value here is 75, so negative 75t times sine b, my b is 367, t, I just need to multiply this whole thing by 1 over 50.2 or divide it by 50.2. We finally have a match, and this is what represents the following circuit. So there you have it. That is how to solve electrical problems by the Laplace transform.